Hey, Honors Physics, this is Mr. Hausman, and this happens to be problem number 12 on page 15a. Many of my classes got to see this in person, but really one or two classes could benefit from a little bit of a walkthrough to kind of see how angled projectiles have to be tackled differently. So regardless of your class, there should be the case that every single class saw this projectile problem, and we started to list exactly some of the assumed knowledge or the assumptions, such as for this projectile, because it starts, goes up to a new height, and then comes back down to the same height, its overall change in y is 0 meters. We know that in the vertical direction, there is a constant negative acceleration, 9.8, but it looks like if we stop here that we are stuck and don't have the ability to work out any more details. So this looks like unsolvable until you realize that the key is in the first moments of the launch. At the very moment that that projectile leaves the bat, assuming it's being hit by a bat, we know that it has at all times a horizontal component and a vertical component. And we have those already labeled, Vx and VIY. But from some of the trigonometry practice, we also know that the VIY is opposite, that's an O, the angle theta. Let's do a kind of a fine tip, right? Theta right here. I don't like that. Let's make that be more of a pinpoint. There we go. Here's theta. There we go. And that's theta. And the Vx is, of course, the adjacent side. O and adjacent. And if you do a quick recall of SOHCAHTOA, and specifically the SO and the CA part, you notice that we use sine anytime we are solving for the opposite side. So in that case, it'll be VIY. And we'll use cosine anytime we're solving for adjacent. And I hope you had enough practice in past weeks on finding components. So let's see if we can't apply it. VIY is opposite, so we're going to use sine of the angle theta, that is 35 degrees, times the hypotenuse, or the actual launch, which is 28 meters per second. And I know you could simplify that down, but we're going to leave it as is. That's an expression that allows you to solve for VIY. Now the Vx on the other side is the adjacent side, so we would use cosine of the angle 35 degrees times the hypotenuse of 28 meters per second. And again, we could simplify that. But what that really did for us is it just now gave us 3 pieces of given in the vertical, and 3 out of 5 is kind of the magic number to start. In the horizontal, we only have Vx. We do not know delta x. In fact, that is what we are trying to solve for. So it looks like we're going to be doing, and the strategies are the same, we're going to be solving for time in the vertical, bring it over to the horizontal, and we'll do it in 2 steps. So consult your equation card, and hopefully you recognize pretty quickly, we've used this a lot, that delta y is equal to VIT plus 1/2 AT squared. And this equation is easily substituted into 0 meters equals sine of 35 times 28 times t that I don't know, plus 1/2 negative 9.8 t squared. From there, I'm going to suggest you do some simplifying on your calculator. Sine of 35, close parentheses, times 28, and you get 16.06 t. And then we have minus 4.9 t squared. That looks like a much more manageable equation to solve, but some people have told me that that's still not something they're as familiar with. So you don't need to use the quadratic because in this case, the constant term is 0. What you can do instead is you can rearrange this formula and you get positive 4.9 t squared by moving it to the other side equals 16.06 t. And I hope you recognize that when you have t squared and t, you can multiply by 1 over t. Some people would just say divide through. And you're now down a t on the left side, and it's gone from the right side. So now we just have 4.9t equals 16.06. 16.06 divided by 4.9, and we get a time equal to 3.27755,102 seconds. It's a little tedious to write out those extra sig figs, but remember, that's not a final answer. That's like a stepping stone. We're jumping across a river. This is the stone we're going to land on, and then we're going to jump again, and we're going to do all of these problems in 2 steps. So if you're a kind of a pattern person, let's put that in, 3.27755,102, 3.27755,102. And what we now see is that we can use our constant velocity, or horizontal velocity equation, equals Vx equals delta x over t, solve for delta x by cross multiplying, and cosine of 35 degrees times 28 times my time from above, 3.27755,102 seconds. But on my calculator, I just left that time right there on the screen. So I just merely need to multiply it by cosine of 35, close parentheses, most common mistake, times 28. You can do it in any order. It's all multiplication. And you should get a delta x of 75.2 meters. And that's exactly what you get using the range formula. But the reason why this process in 2 steps, it's not superior, but what it does is it allows you to be able to solve many different problems because it uses the same strategies that we've been using for all projectile launches. The only thing new today is, let's bring up a laser pointer, is that now we have to do trigonometry to find VI from the V naught, and we also have to do cosine trigonometry to find the Vx component. After that, it really is the same kind of setup. So I hope that helps. Have a great day, guys.